Today we're tackling LeetCode 1252. Cells with odd values in a matrix. The challenge is to efficiently determine the final count of odd-valued cells after a series of increment operations. Can we do this without simulating the entire matrix? You're given matrix dimensions m and n, and an array of indices. Each index pair, say row R and column C, means you increment every cell in row R and every cell in column C. After all operations, we need to return the total number of cells in the matrix that have an odd value. The core task is to count these odd cells efficiently. The straightforward approach is to simulate the process directly. Initialize an m by n matrix with all zeros. Then, for each index pair in the input, iterate through the specified row and column, incrementing each cell. Finally, traverse the entire matrix to count how many cells hold an odd value. This works, but it's inefficient. For every index operation, we're iterating through an entire row and an entire column, repeatedly updating cells. This leads to a time complexity of O of m times n times the number of indices, and space complexity of O of m times n for the matrix itself. The key insight here is that we don't need to track the exact value of each cell, only its parity, whether it's odd or even. An increment operation changes a cell's parity. If a cell is increment an odd number of times, its final value will be odd. If increment an even number of times, it will be even. Instead of a full matrix, we can use two separate arrays, one for row increments and one for column increments. Let's call them rows and cols. When an index pair R, C comes in, we simply increment rows at index R and cols at index C. After processing all index pairs, the total number of times a cell at R, C has been incremented is simply rows at R plus cols at C. We then iterate through all possible m by n cell positions, calculate this sum, and check its parity. If the sum is odd, we count it. This avoids repeated matrix traversals. Let's trace this with m equals 2, n equals 3, and indices 0, 1, and 1, 1. Initialize rows as an array of 2 zeros, and cols as an array of 3 zeros. First index, 0, 1. Increment rows at 0, making it 1. Increment cols at 1, making it 1. Next index, 1, 1. Increment rows at 1, making it 1. Increment cols at 1 again, making it 2. Now, rows is 1, 1 and cols is 0, 2, 0. We iterate m by n. For cell 0, 0, rows at 0 plus cols at 0 is 1 plus 0, which is 1 odd. Count. For 0, 1, rows at 0 plus cols at 1 is 1 plus 2, which is 3 odd. Count. For 0, 2, rows at 0 plus cols at 2 is 1 plus 0, which is 1 odd. Count. And similarly for the second row. 1, 0, rows at 1 plus cols at 0 is 1 plus 0, which is 1 odd. Count. 1, 1, rows at 1 plus cols at 1 is 1 plus 2, which is 3 odd. Count. 1, 2, rows at 1 plus cols at 2 is 1 plus 0, which is 1 odd. Count. After checking all cells, we find a total of 6 cells with an odd value. This is correct because every cell in the example receives an odd number of total increments, making all of them odd. You'll spot this pattern when you're asked to count final states of cells or elements after repeated operations, especially when the operations are cumulative or affect entire rows/columns. If the problem only cares about a property like odd/even, rather than the precise value, think about using parity or separate accumulators instead of a full simulation. The time complexity is O of m times n plus the number of indices, as we iterate through indices once, then through the m by n matrix once. Space complexity is O of m plus n for the two auxiliary arrays. This parity trick is a common optimization. Try the next problem to see if you can apply a similar pattern. Don't forget to like and subscribe for more efficient solutions.